So here is my HPLC concept map. We have a legend on the left. The legend shows that different colored boxes are for the different types of parameters, with their corresponding colors having arrows to show their primary links. The linking responses are in the black boxes, while the responses are on the bottom of the concept map in the circles. The more important main links are bolder than the normal arrows. The parameters are divided into chemical and mechanical. Chemical parameters have droplets on top of them, while the mechanical parameters have cars. The responses are also ordered in their response importance from 1 to 5. The column parameters are particle size, length, pore size, diameter, and ligand, shown in the orange boxes. The equipment parameters are flow rate, percentage B, temperature, wavelength, and injection volume in the dark gray boxes. The mobile phase parameters are pH and B-type in the light gray boxes, while the sample parameters are sample concentration and solvent type in the purple boxes. The main responses are on the bottom of the concept map. These are back pressure, runtime, resolution, sensitivity, and peak tailing. To start off, we're going to have a look at resolution as it's the most important response and what factors will affect it. Resolution is how well the chromatogram peaks are separated. The theoretical equation shows that resolution is a function of retention, selectivity, and efficiency. Selectivity affects the largest change in resolution. It is quantified by the selectivity factors, which is determined comparing the K values of two peaks. This is affected only by chemical parameters, as K1 and K2 must be changed disproportionately. This is connected to retention factor. There are two types of retention factors, gradient and isocratic. These will depend on the method on which you run the chromatogram. This will be discussed in the method development flowchart. The isocratic K are affected by retention time of both the retained compound and the unretained compound such as uracil. It is usually accepted that this value should be under 20. Gradient K is outlined in the equation. It's predominantly affected by mechanical parameters such as gradient runtime, flow rate, column volume. It's also affected by %B. Retention factor is connected to retention. Retention is the amount of time a compound spends in the column. It is dependent on the degree of interactions between the compound and the stationary phase and the mobile phase. What I'm going to do is listing some of the parameters that affect retention and selectivity. First off, there's B-type. B-type affects selectivity through unproportional retention changes. This is because different solvents have different acid-base dipolar properties. This can be seen by the solvent triangle shown on the right. Using the solvent properties, you can optimize selectivity by choosing solvents that have large differences in properties. Isotropic method is used to find equivalent allotropic strengths for different B types and hence produces similar runtime. This is connected to retention. Next, there is %B. Each compound has a different multiplying factor, which means that for every increment change in %B, there will be a disproportionate change in K. An increase in %B makes the mobile phase more nonpolar, making compounds become more attracted to the more nonpolar mobile phase. This decreases retention as it is eluted faster. So this is connected to retention. Next off, we have pH changes. This changes the ionization state of the compounds, which alter their affinity for the stationary/mobile phase. Next is ligand type. This changes selectivity as the stationary phase ligands and sample compounds have different properties. This causes them to react differently depending on these properties. There are a combination of interactions which can be seen on this diagram. So these are some of the factors that affect retention factor, and if disproportionately, selectivity. We are now going to have a look at efficiency, which is another main link that affects resolution. Efficiency is a measure of peak width, which is represented by the theoretical plate number. The theoretical equation shows that the plate height is equal to the length of the column divided by the theoretical plate height, whilst the practical equation shows that n is a function of the retention and width. Retention time is the biggest factor of efficiency, so the last peak eluted generally has the highest efficiency. Efficiency is predominantly affected by mechanical parameters. Band broadening can be seen in the Van Dinker equation. This equation is used to measure band broadening using three main processes, A, B, and C, which give rise to a theoretical plate height. The more band broadening, the more theoretical plate height, which shows less efficiency. A is eddy diffusion. This is where the analyte can take many paths through the column. This multiple path effect makes the band of an analyte broader. Decrease this by using smaller particle size or sphere-shaped silica. E is longitudinal diffusion. This is where the analytes disperse in every direction due to the concentration gradient on the outer side of the band. The peaks are less concentrated and broader. Parameters that affect this are linear velocity and the length of the column. C is mass transfer. This is dependent on pore and particle size and is how much time a molecule spends in the pore. The less time spent, the less lag there is between elution. As we can see, there is a number of parameters that affect band broadening. These include length, particle size, and pore size. Diameter and flow rate both affect linear velocity. A decreaser in diameter causes an increase in linear velocity, such as a finger on a hose, if the flow rate remains constant. Altering the flow rate will also indirectly affect linear velocity. The parameter that affects linear velocity is viscosity, which is the resistance to flow. Percentage B changes viscosity. As the change to percentage B will alter the ratio of A and B. Percent A higher viscosity than percent B. Temperature also affects it, as temperature indirectly affects back pressure and retention time through viscosity. We are now going to have a look at some factors that affect runtime. Runtime is the time taken for a complete chromatography cycle. The time of the sample is injected onto the column until all products have been eluted from the system. There are two main factors that affect runtime. Length, so the longer the column, the further the compounds must travel to elute out. This can be seen in this graph where the retention time of both peak 7 and uracil are increased as the column length increases. Selectivity is also another factor that affects runtime. We are now going to have a look at back pressure and what factors affect this. So back pressure is the difference in pressure between the column inlet and outlet. It should be under 4000 psi for a normal HPLC. It is affected mainly by the column parameters at length, particle size, pore size, diameter, but is also affected by flow rate. UPLC can be used if back pressure is too high. This is because it can handle a stronger back pressure compared with HPLC, up to 20,000 psi, however we have to use different columns. We will now be looking at sensitivity. So sensitivity is the concentration at the peak apex. It can be seen in the equation where the N is efficiency, Vi is injection volume, L is column length, DC is internal column diameter, and K is retention factor. Sensitivity is mainly changed through height, which is the increase in signal height from detector detecting more molecules. This is changed using solvent type, which is the solvent used to dissolve the sample, as this will alter the shape of the peak. It also alters the width. Area under the curve is also altered by the width and the height. This can be changed using wavelength. Wavelength, as different compounds absorb at different wavelengths. Injection volume, as the higher the injection volume, the more molecules that is able to be detected. This can be seen using this graph. As you can see, the higher injection volume, the higher the area under the curve. Sample concentration also changes the area under the curve. Increasing concentration increases the number of analytes that are able to be detected. We are now going to talk about peak tailing. A peak is labeled as tailing or asymmetrical when it deviates from the ideal symmetrical shape of a Gaussian peak. The later half of the peak is wider than the front half. As peak tailing increases, it creates more issues with resolution, quantitation, and reproducibility of the experiment. A ligand can cause peak tailing. This is due to the uncapped lone cyanols, which can strongly interact with basic compounds, causing a longer retention time and peak tailing. Injection volume can also cause peak tailing, as a too high volume can cause overloading and peak tailing. Sample concentration is the same. This is because a too high concentration may also cause peak tailing. So this was a brief overview of my concept map with the parameters affecting the 5 main responses.